everyone, and welcome to another episode of Eyes on Earth. Our podcast focuses on our ever-changing planet and on the people at EROS and across the globe who use remote sensing to monitor the health of Earth. My name is Jane Lawson, and I'll be your host for this episode. Today we're talking about how satellite data will help the United States and Canada manage river water use along the Montana and Alberta border. The St. Mary and Milk Rivers, which originate in Montana, help supply water on both sides of the border. The International Joint Commission, made up of representatives from the U.S. and Canada, is responsible for measuring and apportioning the water. It can be difficult to determine what happens to the water in a system and how much is used for different purposes, like irrigation. But using remote sensing methods to estimate the amount of evapotranspiration that occurs on a field level can help managers understand how much, where, and when water is being used. Roy Sando works as a remote sensing and GIS specialist for the USGS Wyoming-Montana Water Science Center. Roy is the lead physical scientist on the International Joint Commission project and reached out to the EROS evapotranspiration team to use their expertise as a resource. Roy, welcome to Eyes on Earth.
Yeah, thanks, Jane. Really excited.
So first of all, let's talk about the lay of the land in this border area. What is the relationship between the St. Mary and Milk Rivers, and how does that affect water users downstream to the east?
Yeah, so it's kind of an interesting situation. So you've got the Milk and the St. Mary Rivers both flowing out of Montana. And the St. Mary River is a system that comes out of the mountains. So it's fed by glaciers and snowmelt and has a pretty good reservoir of snowpack to feed the system throughout the year. The Milk River, on the other hand, is primarily a prairie runoff system. So it is coming out of the foothills of the Rocky Mountain front and gets most of its water from storm systems or the runoff that comes off of these flatter areas. Despite the fact the Milk River Basin is a lot larger than the St. Mary River Basin, the St. Mary River has a lot more water coming through. The St. Mary River flows out of Montana into Canada and north into the Saskatchewan River and then into the Hudson Bay. The Milk River flows out of Montana into Canada and then back into Montana and ends up in the Missouri River and flowing down to the Gulf of Mexico. So because these two rivers don't actually end up coming back together downstream, there was an interbasin transfer that occurs by taking water out of the St. Mary system and putting it into the Milk River system. That affects water users downstream in a huge way. The Milk River actually would go dry 6 out of 10 years without that additional water from the St. Mary River. Every year by late summer during the dry period, the majority of the water in the Milk River Basin is coming from the St. Mary system. So without that water, without that canal system in place, irrigators would have a lot harder time growing crops and irrigating those crops.
Wow, that's really interesting how the two rivers start in America and benefit everybody along in Canada and America. What are irrigators mainly growing in this basin, and how has irrigation changed over time?
The primary crops that are grown are alfalfa and then hay and other grasses. This is a ranching area. And so almost all the agriculture goes towards sustaining those livestock populations. The irrigation has changed over time, like say the 80s to early 90s. Almost all the irrigation was flood irrigation. The intent is to basically flood your crops. So you've got these crops that are growing alongside the system, the river system. You are basically diverting that and stopping it up and flooding your crops and saturating that soil so that throughout the growing season you'll have enough water to sustain those grasses. Since, I would say, the early 90s, there's been some transition from flood irrigation to sprinkler and center pivot irrigation. And the difference there is that you don't get this big pulse of water that you apply to your crops. You have this sustained, slower drip or sprinkler system that you are applying. This allows you to better match the use of the crops and improve the efficiency. But what it doesn't do is allow that additional runoff that re-enters the system. The plus with the center pivot being the improved efficiency, the greater control over the timing and application of the water. But the minus being that you don't get the saturation as much deeper in the soil. You don't get that pulse of runoff back into the hydrologic system. The amount of irrigation really hasn't changed too much, but you are seeing some of that switch from flood to center pivot and sprinkler.
Let's take a look at evapotranspiration a little more closely in this light. Why is the International Joint Commission so interested in knowing the accurate evapotranspiration rates?
Irrigation is actually an enormous consumptive use of water. In the western U.S., it's the largest consumptive use of water behind thermoelectric. And evapotranspiration specifically is an enormous component in the water budget. So when you're measuring the water budget, it's important to quantify the inputs to the system, like precipitation and sometimes groundwater interaction, as well as the output. So how much water is being withdrawn, how much water is being used for public consumption, irrigation, that kind of thing. You can measure how much water is withdrawn by metering the amount of water that comes out of the system or by stream gauges. But from there, it gets fairly complicated. And those, by the way, are fairly expensive endeavors. So it's not easy to go and install a stream gauge, for instance, or install, a meter on your canal or your withdrawal source. But even if you can do that, it's still more complicated than that to actually measure the amount of consumptive use that is being taken out of the system. In order to ensure that the treaty and the intent of the treaty and the order is being met, we have to quantify how much water is being taken out of the system so that downstream users and all the users along the Milk and the St. Mary rivers are getting a fair apportionment. We still need to make sure that we're approaching this binational agreement and the use of this water binationally in a way that meets what that original treaty had set out to establish.
How did the idea of using remote sensing methods to help understand water use come up? And how is it an improvement over any other previous methods that might have been tried?
Remote sensing and this tool that we're developing, it's going to be another piece of the puzzle, right? It's going to be another tool in the bag, I guess, so to speak, to continue the cliches. And so it's important to understand that this is going to be one aspect of the overall estimate. Remote sensing has been used for a while in estimating things like evapotranspiration and energy balance. My colleagues Gabriel Sané with EROS and Mac Fredericks, they've been working on a project that's called OpenET. This need for an objective and binational approach that's consistent and definitely not reliant on methods that are developed on either side or that favor either side. Landsat doesn't care what side of the political border you're on. It's just recording data. And so we can use this method to take those observations that are objective and unbiased and develop a method to estimate evapotranspiration for the basin. One way that this is an improvement or a potential improvement over the way things were done is it doesn't rely on reporting. Now we have a way to break away from that, have an independent and objective way to check how much water is being used. The benefits of this analysis are going to be directly felt by the irrigators and the resource managers because we'll allow them to improve the efficiency and really have a better handle on what's going on with the water use across their fields and their land over the growing season. So if some areas of their land is not getting as much water, they can adjust their irrigation application rates, or if some of the areas are being saturated and don't need as much water, they can tone that back a little bit.
How does satellite data estimate evapotranspiration?
You can think of temperature as a measure of how much energy is being used on the land surface, right? So when water is converted from liquid to vapor, some of that energy is consumed for the conversion. The use of this energy is recorded and seen or observed by us as a reduction in temperature, and that shows up in the satellite imagery. If you think of a crop that doesn't have enough water, they close the stomata, they stop pulling water up, obviously, and they look hotter in the thermal image. If you take that exact same crop under the exact same conditions and provide water to it, it'll be pulling water up through its roots, through the system, and then transpiring it through its leaves. And then eventually if that water evaporates. And so that process is what makes it look cooler in the thermal imagery.
So what does your role in this project involve? I understand there's 3 phases of the project, and the first one involves satellite data. So tell me about your role.
Yeah, so my role is kind of the overseer of these tasks and kind of just making sure that we're hitting our goals and staying consistent with what's been done. The original model was developed by Gabriel and Mackenzie Fredericks and their colleagues, and they've developed an operational version of their simplified surface energy balance model. And they've processed hundreds of thousands, if not millions, of Landsat scenes and developed growing season ET estimates for the continental US. So we're taking that model and the code that they've developed and modifying it and introducing a couple new data sets to extend into Canada. It's been really nice to have them, as collaborators on this and to kind of not be fumbling around in the dark, so to speak. Another piece of my role is really communicating with the St. Mary and Milk River Technical Working Group, which is sort of the scientific expert panel.
So tell me how the second and final phases are scheduled to play out, especially what the result will look like for the lives of the people who use that basin's water.
The second phase is intended to get out and get our boots on the ground and understand what's actually going on in the basin. Remote sensing is great and an incredible tool. I think it's the way of the future. We can learn so much about these snapshots from space, but it's crucial to actually have an understanding of what's going on the ground and have an ability to calibrate what you're seeing in the satellite imagery with what is actually occurring. So phase 2 is intended to do just that. The goal is to get out and drive around the basin, talk to landowners, talk to irrigators, inventory what irrigation is occurring, what fields are being irrigated, the type of irrigation, the timing of the irrigation, the crops that are being irrigated, the condition of the crops, the condition of the soil. Make sure that we understand all these components so that when we look at those data from the satellite imagery, we can understand what might be causing the differences that we're seeing across the fields, and we can make sure that we're hitting the targets appropriately. So that's phase 2. Phase 3, then, I'll just touch briefly on that because I'm really excited about this. So phase 3 is taking all of what we've learned in phase 1 and 2 and combining it into a tool that irrigators can go and check out their fields or some of the fields in the basin and understand nearly real time, within the month, I would say, how much water is being used throughout the growing season. It's just really trying to give as many people as possible as much information as possible.
Can we touch a little bit, since you mentioned historical, let's touch on the fact that the Landsat satellite data that you were using actually does go back several decades, which is pretty unusual, right, for satellite data?
Yeah, the Landsat archive is incredible. This project is going to be using Landsat 5, 7, and 8, and it will allow us to estimate evapotranspiration all the way back to early to mid-1980s. A lot of changes have occurred in that time period, so we can track how these different irrigation methods affect the overall budget, and it wouldn't be possible without this archive of satellite imagery.
So 2020 was a bit of a challenge for a lot of people, and this project was no exception. I understand that part of the St. Mary Canal broke this spring, reducing water for irrigation from the Milk River, and the pandemic closed the border that this project is centered on. So how did you adapt to these and any other challenges?
With any project, you get some things that you have to overcome that are unforeseen, and this year especially was, as you mentioned, not particularly easy. But the people on the technical working group are incredible. Not only are they really knowledgeable and experts in their field and know a lot about the system and the hydrology, but they're also incredibly flexible and great people to work with. When something like the pandemic came up, we're working closely enough with our counterparts in Canada that we've got our plan laid out. We can have 1 or 2 scientists involved in the work on both sides of the border. But in case that's not the case, we're confident that our Canadian counterparts will be able to pick up the methods. It's all about working with the experts on both sides to overcome some of these challenges. And another challenge you mentioned was the St. Mary Canal failure that really had a huge impact on the water use in the basin. And so actually it kind of allowed us to divert some of the effort in phase 1 to estimating the water use in the basin for 2020 and track how this extraordinary circumstance maybe affected some of the irrigation or some of the water use.
Talk a little bit about the technical working group. Since using high-resolution satellite imagery to estimate field-scale evapotranspiration over this period of decades is pretty new for this, how did they receive it?
It's one of the most collaborative and communicative groups that I've been a part of, frankly. We meet regularly, we discuss some of the projects that are ongoing, and we talk about, ways that this can improve the overall process of estimating water use and how it can help irrigators and land users on both sides of the border. When the idea of using remote sensing came up to estimate evapotranspiration, everybody was on board. They saw the benefit of this, and they're really excited to incorporate this method into the bag of tools that we have.
When do you expect to deliver this tool?
The goal is to have the tool developed by fiscal year 2023. So that means by the end of September of 2022, we're hoping to have this tool rolled out and have an online interactive platform that people can go in and click on their pixels or define their areas of interest and get the results for that area.
Any other closing thoughts today?
I guess I'd just like to end with, again, the importance of the Landsat program. Sometimes it gets brought up like the administrative burdens or the fiscal burdens of the Landsat program. But you think about all the cost savings in the analysis and the efficiency of improving our estimates on things like water use in situations like this. And it's really hard to quantify how much money we're saving by having these data available. It's pretty astonishing the amount of science that can be done with an archive that goes back to the 1980s, and that's only going to become more and more valuable as we progress into the future.
We've been talking with Roy Sando of the USGS about a joint U.S.-Canada water management effort. Thanks for joining us, Roy.
Yeah, it was my pleasure. Thanks a whole lot for having me.
And thank you to the listeners as well for joining us for this episode of Eyes on Earth. Check out our EROS Facebook and Twitter pages to watch for our newest episodes. You can also subscribe to us on Apple Podcasts. This podcast is a product of the U.S. Geological Survey, Department of the Interior.